Okay, so binary images. So binary images are those images that only take two values, one for the foreground and another one for the background. Yeah, here it is this idea that I mentioned that can take whatever values of 0 and infinite, 0 and 1, or 1 and 0, it doesn't matter. So it's only that they take two values. And it doesn't matter how you represent them. So you may represent the foreground in white, you may represent the foreground in black. As long as it is clear that it is the foreground, then there's no problem. And 0 to 55 or to 55, 0. So you don't care about these two specific values. Okay, so along the lecture, we will assume that they take the values 255, 0. So the background is 0. But we will try to be consistent with that, but at some point it might not be. Okay, so given an image, we can define a couple of regions. So the first one is the foreground of the image and the background of the image. So the foreground is a set. This is important. This is a set made of all those pixels whose intensity value takes the foreground value. And the background is just the opposite. So they take the background value. And because they are sets, we can use this kind of set notation and sets operators where we can compute the union of the set. So the union of this set and this set has to be the whole image. The intersection has to be empty because a pixel either belongs to the foreground or belongs to the background, and they are complement of each other. Good. Then, yeah, this is an example where all those pixels are taking the foreground value, and all these pixels are taking the background value. And the union of the two makes the whole picture, and the intersection is empty, and one is the complement of the other. Okay, yeah, you can define it for kind of gray images where you have to binarize them. Okay, so you binarize your image and then you are defining a couple of regions here. So in all these tools that we will define today, we will, this is called mathematical morphology. And we will see it in a couple of cases today with binary images and tomorrow with gray images. So with in this mathematical morphology, one of the key ingredients is this structuring element. So structuring element, you can think of it as a kernel. Okay? So it is like a kernel. This symbol here indicates the origin of the kernel. And then these are the two most typical kernels where it is all the neighbors a given pixel, and this one that is all the neighbors that share an edge. So this pixel shares an edge with this one, that is this one, while this pixel only shares a vertex with this one. Okay, so set 8 is all neighbors sharing an edge or a vertex, and set 4 is all neighbors that share an edge. And then you can define kernels of all kinds. So you can define this kernel, this kernel, this kernel. This kernel is a kind of shifted delta, right? So this is the origin, and this is shifted delta. And here again, just a representation issue. So the kernel, the active values here are darker. So it is just a representation. So this is the foreground, now this is the background. So we don't care how to represent things, but it has to be clear what is foreground, what is background. Yeah.
Do you repeat what are those kernels?
These kernels?
Yeah,
these two? Yeah, so these are, you may define kernels the way you want, but these two are kind of special. They're special because they define neighborhoods that with different properties. Let me go to the whiteboard. So let's say that we have a given pixel, so this pixel, and we highlight all neighbors that share an edge. So all these neighbors, they share an edge with this pixel. Okay. And we make, this is set 8, set 4. There is another way, that is, you consider this pixel and then all neighbors that share something, an edge or a vertex. Okay. So this one and this one, they share this vertex. This, I will use different color for that. So these are the same, that share edges, but then we may also define those ones that share a vertex only. Okay. So this is, if you want, this is a strong connectivity. This is the, or this will define strong connectivity, because these two pixels are stronger connected than this pixel, and these are a pixel, these are a neighborhood. This is defining a strong and weak connectivity. Okay, because there are points that are more weakly connected. Okay. So the structuring element is used in the same way as kernels. So what do we do with kernels? Look at convolution, for instance. So when we have a convolution, what we say is I have an image, I convolve it with, let's make them discrete. So I convolve this image with a kernel, and then what I'm doing is I have a big image. So I have a big image. And then this kernel here is moved around this. So I center the origin of the kernel somewhere, and then I do some operation there, and then I shift this. I shift this origin to some other place, and I repeat the same operation, but now it's another location. So you move the kernel around. So we will do the same now, but with these extraction elements. So with these extraction elements, they also have an origin, and then you shift your kernel to wherever you want to do your operation. And we will denote that thing as, so set will be the extraction element, set plus P will be the kernel shifted to the location P, to the pixel P. And we can define the neighborhood. So we can define the neighborhood of the image I with the structuring element set at the location P. So it is simply this. So this is the structuring element shifted to that location. And this set here, down here, is the neighborhood of I. So this is I, the whole thing is I. But the neighborhood of I at the location P, according to the extraction element set, is just this set. Okay, so it is the small set, the small subset of the image that is covered by the shifted kernel. And the right word is not kernel, it is extraction element. So in this theory, we don't talk of kernels, in convolutions we do, but here we talk of extraction elements. Then we can also, in the convolution, let's look at the convolution again. So when we compute this convolution, this is the sum overall. We use a dummy variable that we will call R prime. So it is I at R prime, and then the kernel at R minus R prime. And we know that this operation here, it is a reflection is a reflection of the kernel. And this reflection is caused by this minus sign. And this is a shift. So we have to first reflect the kernel and then shift it to the location I. Okay, so let us define reflections, but now with the structuring elements. So we have the same. So we have the structuring element whose argument is reflecting. So it is this minus r prime that I was using. And the reflected kernel we will denote with this inverted arc. Okay, so this set with inverted arc is the reflection of the kernel. So if you have this kernel, this is the reflection. You have this kernel, this is the reflection. So reflection, this minus r is do it here. So if you have minus r, so if you have a kernel here, so this is a set, and then set this thing is this pixel here goes here. So the origin stays, but then all the other pixels are reflected. So this pixel goes here, this pixel goes here, and so on. And so everything is reflected. This one goes there, and so on. Okay? So, and this is set of minus r. So it is the reflection. So there is a mirroring in both directions. So there is a mirroring in this direction and there is a mirroring in this direction. This is the mirror with respect to a point. Okay, good. Okay, so we can define the reflected elements. And now we will start constructing our operators. So let us go back to the convolution again, because the convolution we know better. So we have convolution is an operator. It has a left-hand operand and a right-hand operand. So you take two elements, so two images, and you operate them. So we will do the same, but now our operators will be different. So will be defined in a different way. So we will have an image that is binary, and we will, for instance, let's say this is the dilation operator with a kernel. How do we define that? Okay, so the dilation, the final effect will be this. So you start with this, and this will be the final effect. And here we have highlighted what is the difference. So what we are doing is taking the foreground and dilating the foreground. Okay, good. Then we will define it in this way. So actually we have three different ways of defining it, and this will be our symbol for this operator. So an image dilated by a structuring element will be, this should be set, not be. Okay, so it will be a set such that all those pixels in the support of the image, such that when we shift the reflected kernel to that location, intersection with the image, it is different from zero. Okay, so let's look at that. Here. So we have the original image. I have to shift my kernel everywhere. And for every location, I will check whether the reflected kernel intersection with that image. So the image is just the set of pixels in the foreground. So this one intersected with this is different from the empty set. So when I shift my kernel to here, so my kernel will be select. Okay, so it is just a 3 times 3 square. So when I shift it to here, the intersection of this kernel shifted with the image is empty. There is no intersection. And then that point there will not belong to the dilation because the intersection is empty. And then when you move fully inside, the intersection of this shifted kernel with the image, now the intersection is not empty. So this point belongs to the kernel, to the dilation. What about this one, for instance? So these points here, they don't belong to the image, but if I superpose the kernel there, the structuring element, I compute the intersection with the image, the intersection is not empty either. So these points belong to the dilation. So the final effect is that the foreground is dilated by the shape of sedate. Okay, so all these channels, for instance, this channel here is filled, this channel here is filled, empty points are also filled, you see? Here we have the original and the dilation both together. So all these yellow points, they have been filled by the dilation. Okay, this is not the only way of defining the dilation. They are all equivalent, but I think these are the two. They are more similar to what we are used with the convolution. Okay, so let's look at the convolution again. So we have the convolution here. So let's go for the convolution again. So we know that the convolution can be defined in this way, or it can be defined in this way. Sorry. Okay, so this is so here in this one, image stays fixed and the kernel moves. Here, this one, the kernel is fixed and the image moves. So the kernel stays fixed. It is the one going with R prime. And the kernel and the image is the one that is moving. So we have here two ingredients. So the first ingredient is movement. So this is the movement. Sorry, I want to use a different color. This one. This is movement. Okay, so this is the one moving. And for every shifted image, what we are doing is we are multiplying. So we are multiplying, and then we are adding. Okay, so we are combining. This is just combining all these different shifted versions of this image. Okay, so let us look at the dilation in that way. So another way to define the dilation, they are totally equivalent, the result will be the same. It is, you take the kernel, you move it to all the locations where the image I is. So you go this could be, let's say that your image is binary. Okay, so let's say that your image, running out of space. Yeah, here I will do it. Okay, so let's say that this image is binary. So it only takes the values 1 or 0. Okay, so you could rewrite this in this way. You could say this is the sum of all R prime belonging to the set where image at R prime is equal to 1. This is the foreground. And then this is 1. H of R minus R prime. Because the image takes value 1. And so this image only takes two values, 0 or 1. So if it is 0, it doesn't matter because I'm multiplying anything by 0. So I can remove those zeros. And then I can only concentrate on those locations where the image is different from 0. It takes the value 1. And then I can shift my kernel to those locations and combine them. And the combination here is sum. When we are talking of sets, combination is union. Sum and union, they're very much related. They have very similar properties in some way, algebraic properties. So this is a convolution, kind of convolution, but now with binary images. And I can do the same. I can interpret this in the same way. So I can say this is the sum over all R prime belonging to the set where now the kernel is different from 0. So where the kernel is 1. Sorry, this is not a vector. This is not a vector. So where the kernel is 1, but now of the shifted image and times 1, because the kernel also takes only value 0 or 1. So either I shift my kernel or I shift my image. So I can now go for the support of the kernel, of the structuring elements, shift the image to those locations, and combine all those images. So this combination is the union. So dilation is kind of convolution, but for binary images. And yeah, so here we can see, so in the definition, we were using the first definition, we were using this reflected element. Okay, so if it is a kind of convolution, we should expect that if I take an L and I convolve it with a delta, what is the delta here? I convolve it with a delta, I should get an L, because that is one of the properties of convolution. So anything convolved with a delta is that thing. So we invert our structuring element, this is the 1, and we will move it to all places where the intersection between the inverted element and the delta is different from 0. And the first picture where that happens is this one. So when you shift this origin to here, the intersection between this set and the delta is different from 0. And we will highlight it there. And then we look for some other place where the intersection is also different from 0. This is one such place. And we keep it there. And you keep moving for all points where the intersection is different from 0. This is the last one. And then when you look, what is the shape of the object that you get at the end? This is the shape of the object. So you have an end. So you have a structuring elements that looks like this. You compute the dilation with a delta, and then what you get is your structuring element. So it behaves like the convolution also. Okay, yeah, this is just a fast way of computing that. So this is, you take the image and you shift it to all places where the kernel is different from 0. So you can compute it using the first definition, and it would be these intersections that we have been computing here. But you can also use that other definition, this other definition, where you're moving the image. So what we have to do, let's say that we are convolving this D with this kernel. Okay, this kernel that is separated, so it is 1, 0, 1, 0, 1, and so on. And then what we have to do is to shift the D to the locations of these different deltas. So first I move it to the location to this delta. So this is shifting it 2 pixels to the left, 2 pixels to the up. So I shift it 2 pixels up, 2 pixels to the left, and then only 2 pixels up, and then shift it 2 pixels up, and then 2 pixels right, 2 pixels up, and so on. So you have the different versions of the data, and then you have to combine all of them. And the combination here, it is not adding, it is union. Okay, and yeah, this is another example. So at the end, this union, what makes you is this result. Okay, so here is another example. So this is the original, and then convolved with, or not convolved, dilated by this kernel, and then we have the different versions. So we have this pixel here tells you you have to move it 1 pixel to the left, 1 pixel up. So you shift your image 1 pixel to the left, 1 pixel up. So we have it here, and then 1 pixel to the left, 1 pixel to the left, down, and so on. And now you compute the union of all those sets, and this is the dilation. And we should see things like what happened before. So we have an isolated delta. So this delta, at the end, what I should have is the delta convolvement with my structuring element, that is this thing here. And in some other places, it is more difficult to see. So why this thing is filled. But okay, it results from the convolution, from this dilation. And in some places, it is very easy to see what the dilation has done. Now erosion. Now it comes your question. So erosion is the opposite. So instead of making something bigger, the foreground bigger, we will make the foreground thinner. So let's say that this is our image. We make it thinner, and then this is what we get. Okay, and here we have the superposition of the two. Okay, so how to make it thinner? So this will be the symbol that we will use for this operator, and it is. So it is another set that is made of all the pixels in the support of the image, such that the kernel shifted to that location is completely included in the image. And let's see some example. Let's say that I use again this kernel that is 3 times 3. So it is the fully connected kernel. This is my image. And now I shift my kernel to this location. So it is fully contained. So this point will belong to the eroded image. Let's move it to here. So when I shift my structuring element to here, none of the pixels of my shifted kernel are included in my image. So this point here will not belong to the eroded image. What about isolated pixels? So for instance, this one here. So these ones here, I don't understand why they're shown there. So let's move it to here, to this one. Okay, so when I move it to here, my kernel is not fully included in the image. You see? So this point should disappear. Yeah, actually, that's right. This is not coming from this one, but it's coming from the middle of this part. Okay, so these points here, when I shift my kernel to the middle of this part, they are fully included in my original image, so they stay. But when I shift them to here, they are not fully included, so they disappear. Okay, so and here we have both superposed, and there is something that we can already note from these operations. So this is dilated, this is the original. The original is fully included in the dilation. So this one with this kernel, okay, with this kind of kernel, depends on the kernel, but with this kind of kernels, the original is fully included in the dilation. And in the erosion, it is the opposite. The erosion is fully included in the original. And yeah, so this is one way to define it. And then there are two other ways. So there are two other ways that kind of use the same ideas for the convolution, but now they are more general. So it is the same. So either we move the kernel to the locations where the image is different from zero. It is not the kernel, it is the reflected kernel. And then we have to combine. But the right way of combining now it is the intersection. It is not the union. And here it is the same. So either we move the kernel or we move the image. So we move the image to the locations of the support of the reflected kernel. And so we shift the image, and again we have to combine, and the combination here is an intersection again. So now this is a kind of generalization of the convolution. So we have generalized the kind of stuff that we can do with convolution. Convolution is just one way to operate a couple of images. We have seen two other ways. One is similar to the convolution, the other one is not similar to the convolution. Yeah, so here we have the three of them. So we have the original, the erosion, and the dilation. And with Z8 is this fully connected structuring element. So we see that the erosion is fully included in the image, and that the image is fully included in the dilation. Then we have these properties. So these properties are similar to the. So we have used unions and intersections. Do you remember Morgan laws of sets? So we had something called Morgan's laws. Do you remember that? They were saying something like, let's say that I have the union of something. I can feel this is the complement of that set. This is this one complement. So it is the complement of A intersection with the complement of B. And we have the same, but now with intersection. So it was the complement of A union with the complement of B. Now we have the same kind of laws, but now with dilations and erosions. And they're not exactly the same as Morgan laws, but you see the complement of the erosion, it is the complement of the first one, dilated, and it should be the total analogous to the Morgan laws would be the complement of set, but it is not the complement of set, it is the reflection of set. And here we have the same, so the complement of the dilation is the complement of the image, now eroded with the reflected structuring element. Okay, so they are equivalent to the Morgan laws. So it is the complement goes to each one of the elements, except for the kernel that is reflection rather than complemented. And then the operation is just the opposite. So dilation and erosion, they are kind of complementary operations. And then deriving these ones from these ones, it is trivial. So it is the complement of the complement. So you take this one, compute the complement. So the complement of the complement is whatever is inside, and then you take this one and complement it. So this is trivial. Very good. Now we can define another another set of operations, a couple of more operations that will be opening and closing. So opening is this one. It is first you erode and then you dilate. And the closing is first you dilate with the reflective extraction element, and then you erode with the reflective extraction element. So now we define these two operations. Well, let's see what we can do. So for instance, this is the result. So you take this image, first you erode and then you dilate. So when you erode, all this area disappears, and then when you dilate again, you only recover this part. So this is opening, and here is again with the structuring element 8. So first you erode, you have the original in white. First you erode, you get the pink one, and now you dilate. So what have we got? So we have got all these isolated pixels, they disappear from the erosion. When you dilate again, you don't recover. You cannot recover these points because these points have disappeared from the erosion. And again, with sedate, the opening is fully included in the original. And yeah, this is the same now, step by step. So you take the original, first you compute the erosion, and then you dilate. And then isolated pixels or very thin structures, they disappear. And this is opening. So it is the process of opening is the best approximation of I that can be made by taking the union of translated copies of the kernel, subject to the constraint that the opening is fully contained in the original image. So you have this image, and you wonder, what is the best approximation that I can do to that image, such that my kernel is fully included in the image. This is the one. So if I shift my kernel to here, they are not fully included. So that's why these regions disappear. The closing is the opposite. First you dilate and then you erode. Okay, so for instance here, it can be used to fill small gaps. So you have the original image is here. First you dilate, and then this pixel is filled, for instance, and then you erode. Okay, so let's. Next slide, we have the three. So we have this original. First we dilate, then we fill all these empty regions. All these are filled. Okay, and this channel here, this one, and then you erode. And when you erode, that is what. So closing is a way of filling gaps. And filling gaps in the foreground. Opening can be seen as a way of filling gaps, but filling gaps in the background. So opening, if you think in terms of the background, from the background point of view, this is a gap. This point is a gap. So I have background, and then a foreground, and then background again. So this point is a gap from the point of view of the background. So opening is a way of filling gaps, but from the background perspective, while closing is a way of filling gaps, but now from the point of view of the foreground. So from the point of view of the foreground, this is a gap. So I have foreground, then background, and then foreground again. So I can fill it. With the closing.
But in the slides it says that the opening is the approximation of the foreground, not the background.
I haven't said that it is the best approximation of the background. I have said it is a way of filling gaps in the background. So the mathematical property is that it is the best approximation of the foreground that can be done by union of translated copies of this with the constraint of being fully contained. So you see there are two different descriptions. So those are two different properties of the same object. Yeah. And then we also have kind of these Morgan laws, but now for the opening and closing. So these were the two properties that we had for the erosion and dilation, and now we have two new properties, but now with the opening and closing. So the complement of the closing is you have to complement the first one. The second one behaves a little bit especially with respect to the structuring element. So we don't have to compute the complement, and the operation is reverted. So if this is closing, this is opening. If this is opening, this is closing. So, but it has the same flavor as the Morgan laws. Now it comes to a question. So how we get from the original images to all these different versions? So it is just following those operations, but you have to do them very carefully. So the only one that is more that is similar to convolution is this one, dilation. All the others are a little bit more complicated. But we have seen how each one of them behaves. So it is the same that we have been doing before.
And I don't really understand the erosion, the white point.
Yeah. So erosion, we have said it is making the foreground thinner with respect or with the shape of the structuring element. Okay, so if I make this one thinner with this shape, it disappears. This part there, it is more difficult to see, but it seems that when you do the erosion, sorry, this one. So when I do the erosion of this with respect to this shape, it disappears because I cannot fully, so it is, I have to shift to everywhere where it is fully contained. If I shift this to here, it is not fully contained. If I shift to here, it is fully contained. So I have a delta. When I shift it to here, all these points, they are not fully contained. Okay. Again, border effects. So when you reach the border, all these intersections and these things, they are not well defined. So there will be a region around the border where you have to take decisions. But also, we can use these operators to extract boundaries. So for instance, let's say that we have this binary image. So we have this binary image. We compute an erosion by a square. So this square is this 3 times 3 fully connected structuring element. And this is the erosion. Okay. And now we compute the difference between the original and the erosion. And this is what we get. So what we get is a boundary. So all these pixels in the difference, so are the pixels that are in the image but not in the erosion. So all these pixels in the boundary are inside the object. So you see all these pixels, they were originally in the object. And they also have another property, that is that they are 4 connected. So 4 connected, this 4 connection is that when they share, so they share edges. Okay, so all these points, they share edges. Here they don't, but it is kind of by chance. So all these, the boundary is fully connected with 4 connected. So these two would be 2 different boundaries. So this is one component of the boundary. This is another component of the boundary, another component. We have the boundary has different parts, and within each part, it is fully fork connected. So fork connected is this kind of connections that we have. Here. This is the fork connected neighborhood. Okay, so now we can compute boundaries of images using this kind of operators. So you can take a binary image, compute the notion, you compute the difference, now you have the boundary of your object. So let's stop here, and then we make a 10 minutes break. Volvemos a Lec23. Sí, el día 3 siguen trabajando en la práctica, tienen que entregar al siguiente para nosotros. ¿Qué tal lleva la práctica?
Sí, te iba a comentar que no hay, porque no sé, no es mi tamaño, entonces ¿qué haría?
¿Qué hace?
La última vez que vine me dijiste que era como un paper, estábamos haciendo un paper, y no sé si la práctica...
Un paper no, o sea, tienes que leer de algún paper,
me dijiste
y
como...
tú tienes que hacer un informe y hacer una presentación.
Vale, pero ¿y eso es lo que llamamos práctica?
Sí. Tiene dos partes la práctica, pero la segunda no es obligatoria. Y luego, pues, bueno, tiene tres partes. Esa es una, que es la más grande. Ese sería como el 70%, y las otras dos no son obligatorias. Un 15% sería aplicarlo tú a imágenes tuyas. Yo he cogido mi imagen, lo he corrido esto que te he explicado, y mira lo que me sale.
Claro, porque el año pasado recuerdo que había compañeros que sí hicieron código...
Claro. Y el otro 15% es hacerlo tú, un código.
Vale.
Pero ya esas dos partes no son obligatorias. Es obligatorio, pero claro, te dan un 7.
Vale, o sea, lo principal es eso, de coger el tema, exponerlo, preparar la presentación y exponerlo.
Eso, con eso llega a un 7.
Vale.
Y si quieres sacar más, pues tienes que aplicarlo a imágenes tuyas, y si quieres sacar más todavía, tienes que implementarlo. Yo te llevo la práctica 1. Bien. Y vas avanzando, ¿no? ¿Cuál es tu nombre? Se me ha olvidado.
Ignacio.
Ignacio.
Hola.
¿Tú te llevas la práctica, Sancha?
Bueno, ahí voy. ¿Cuántas hojas tiene que ser en total, más o menos?
20, 30.
20, 30 citas. Otra cosa, te quería preguntar si me podías subir un momento la pantalla porque lleva un momento está bien y no da tiempo a copiarlo.
¿Es la pizarra?
Sí, claro.
Aquí.
Sí.
¿Toda la pizarra o...?
Vale, sí, vale. Para quitar
Sí.
este momento. Vale. Entre 20 y 30, ¿no?
Hola, Carlos, ¿qué tal?
Hola.
Que es que iba a llegar tarde y me he quedado fuera.
No tenía chiste preparado.
No, mejor me he quedado fuera. Que es que eso, que tenía una semana que está en la de curro, pero muy bien. Yo la práctica ya la y estoy en efecto, al final me he conseguido comenzarlo en julio, o sea,
Tienes que sacar esta asignatura.
No, o sea, me puse las pilas, es verdad que fui un poco pillado por eso, por el ritmo, pero bueno, bien. Y después la práctica no. Es verdad que la parte de programa puedo ir bastante más lento, pero bueno, como ya también me he pegado con bastante lenguaje, ¿sabes? El programa con parte de poner un pelín mejor, pero eso que es lo más dentro de todo. A ver qué tal. Yo creo que lleva todo porque encima me lo he fileteado mucho, tengo el 6 de mayo, el 7 de mayo que tenemos, el examen, y el 7 de mayo lo viene.
Solo te queda esta, si no es
no puedo perdonar y iniciarlos más, claro. Sobre todo porque si no me presento el o sea que... Claro.
Esta asignatura creo que se puede inserir en la segunda.
Sí, gracias. Que no puede venir a verlo, pero sí, la preguntas que me van a dar.
Yo voy directo desde allí a...
Los vídeos de los de una de las más y esperamos que vamos a preguntarse ahí y paso mañana para ponerle fórmulas.
Ahora sí de pueblo. Mi casa está en catedral. No voy quedando en plan casas de niños. Ahora está en invierno. Está bien, bueno. Ya debería la semana que viene a Madrid. Tengo reuniones. Y mi madre tiene como el 26 de mayo, pero Barcelona me quita. Ya. O sea, sí que quiero ir por el pasando para ver si eso se podría,
¿Los sacan en 3 días?
sí, se ve que sí, como ya tiene un
¿Tenemos
costo.
teórico o así?
Sí, pero lo puedes hacer por internet.
A ver, bueno, eso ya tenemos que
Ahora me gustaría porque son de milagros.
entonces también
Que yo parece que hace varios años. La que te pones hermanas de no sé
Vamos por la plaza, este era un estrella, Sí.
bueno, yo me acuerdo que era la última clase. La última clase de señales no sería más.
Okay, so let's continue. So we have seen one of the applications of these erosions, that of these operators, that is extracting boundaries. And we will extract boundaries in more ways. So here is computing the erosion with set 8. So what happens now if I compute the erosion with set 4? If I compute the erosion with set 4, now what I get is an 8 connected inside boundary. So now these boundaries here, they are 8 connected, so they can be connected. Otra noche, que anda, Ignacio.
un chiste.
Claro, el que llega tarde cuenta un chiste.
¿Cómo se queda un mago después de comer? Magocito.
Okay, so when we compute the erosion with set 4, now the inside boundary is 8 connected. So now they are allowed to have this corner connection. And here is the now let's compute a dilation with set 4. This is this plus sign. So dilation with set 4. And now we compute the difference with the binary, with the original. So again, we have an 8 connected outside boundary. Now the boundary is outside the image. It is not inside the image, it is outside the image. If we do dilation with set 8, and then we compute the difference, then we have an outside boundary that is 4 connected. So all the pixels share an edge. Yeah, these are some properties. So the 8 connected inside boundary is inside the 4 connected inside boundary. The 8 connected outside boundary is in the 4 connected inside outside boundary. And yeah, so there are these really, okay, so we don't care about all these properties. But these are interesting ways of now computing boundaries that are inside, boundaries that are outside with different properties and so on. I can also compute the boundary within a region only. So let's say that I have this image. I want to compute boundaries in this region. So what I can do is I can compute the dilation, but compute the dilation only inside this mask. So I compute the dilation everywhere, and then you mask it. You mask the whole dilation. This is the mask dilated. And now you superpose this union with the original. So now you have computed a dilation conditional to some region. So only a dilation only within a region. And another very useful thing that is that with these operators we can extract connected components. So a connected component is something, they are well delimited objects. So here in this image we have a couple of objects, this one and this one. How can we make an algorithm that identifies those two objects? So we will put labels to these, or tags to these objects. So at the beginning, none of the pixels is tagged. Then we take one of the pixels that is untagged, so let's say this one, and we start doing the following. So first we dilate. So tag means this is object number 1. So now we dilate the tag. This is the mask dilated tag. So, and now we use the original image as mask. Okay, so we compute all these. So this dilation we restrict to the region of the original image. And now we have all these two other pixels. These two other pixels have the same tag as the original one that originated the dilation. So this is object 1. These two other pixels, they will also be labeled 1. And now we dilate again, and we compute the mask. These two other pixels will also gain this object 1 label, and then we dilate again, we compute the mask, and now they get the label 1, we dilate again, and we mask, and at the end, all these pixels, they get label 1. And if you dilate again, you don't gain any other pixel, so it stays fixed. So you have finished with object 1, and now you go with object 2. So you go to another pixel that is unlabeled. So you take this one, and you keep doing the same thing. So at the end of all this process, what you will have is object 1 separated from object 2, and you would know all these pixels belong to object 1, all these pixels belong to object 2. And we can also use another application is to do these binary reconstructions. So binary reconstruction is, let's say that we have this original image. And how have we got to this image? By thresholding, for instance. You take an image, you put a threshold. Everything above the threshold is 1, everything below the threshold is 0. And then, so you get most of the object that you want. But there are some few pixels that are not by chance, but maybe by noise, or maybe they really have those values, but they are disconnected from this object. So how can I recover the main object that I'm interested in? So I can do the following. So I can take the original and remind opening is filling the gaps from the point of view of the background. So all these points would disappear in an opening. But I have also lost a lot of useful information. So can I design another operation that keeps the interesting part but fills the gap in the background? This will be the reconstruction. Okay, so the reconstruction is the following. So first you erode. Sorry, this is opening. So first you do opening, and now you will iterate here. So this will be your initial step. So now what you do is you dilate with set 4 or set 8. Now you compute the AND between the original and your current state. And if it is not stable, so if the image has changed, then you update your current state and you repeat. And you repeat this process until the image doesn't change anymore. So when it doesn't change, you have finished. So with that, so if we start with the opening, and now we compute the and between this one and this one, we compute the dilation, and you keep doing that, opening, dilation, and until it stays, until it doesn't change anymore. And you see, you have recovered many useful parts of the original image. So, very useful thing. Another useful thing is this skeletonization. So skeletonization, here we don't have any image. Let me look for one. So we will use here image, binary image. So this is the kind of stuff that we want to compute. So given a binary image, we want to compute what is a kind of graph that connects everything, and that gives me the shape of that. So if I have this horse, I get this skeleton. If I have this person, I get this skeleton here. If I get this hand, I get this skeleton. So this is what we want to achieve. So how to get that? Do the following. So the skeletonization of an image, so this will be the skeleton, will be the union of many skeletons. And these skeletons, these other skeletons, they will have a radius. Okay, so that is this radius. We will have disks of radius r. Okay, so what is a disk? Okay, this is also something interesting to think. So we are used to say, okay, disk is the other point. This is a disk. All this content is a disk. So how would you define this? So given a location R0, so the disk of radius r and center R0 is a set of all points in R squared such that the distance between that point and R0 is smaller than modular. Okay, so this is the definition of the disk. Why our disks are round? Because we are using this distance. So the distance between a pair of points, for us it is this. It is square root of rx minus r0x squared plus ry minus r0y squared. This is our definition of distance. And then that definition of distance makes this disk to be round. What happens if we have this definition of distance? So the distance of r and r0 is rx minus r0x plus ry minus r0y. That is another distance. So what happens if I compute that distance? Then disks are not round anymore, they are square. So this is the disk, this is this disk according to this distance. So this is an interesting change of mind. So the shape of objects depends on what is your definition of distance. Okay, so the kind of distance that we are using for defining this disk is this square distance. Okay, so we will have a disk of radius r located at P. So we will compute many skeletons So a point, a point belongs to this skeleton of radius r if it is the locus, so if that is the center of a maximal disk of radius r that is fully contained in the image I. So let's see an example. I think it is easier than in words. Okay, so this will be the result. Okay, so let's we will see later how we get to this result. But let's say that we have this image, and then at the end we will have this skeleton that is fully connected. But the raw skeleton, the one we have defined in the previous slide, will be this one. Okay, so how to get to that? Okay, so let's look at no maximal disks. Okay, so all these blue points, they are no maximum. Why? Because let's think of this one. I can find another disk that is bigger than this one, and that fully contains this one, the blue one, although it is located somewhere else. So if I can put it here, I can draw a bigger disk. Okay? And the same happens in all these blue points. You can always find another disk that is bigger than this one, and that contains fully this one. And here you have the corresponding ones. So for this blue disk, this red one is the one that fully contains the blue one, and that is bigger than it. For this blue, you can find this red one that is bigger than the blue, and that fully contains the blue, and it is fully contained in the image. Okay, so now we look for all the points that define are the centers of maximal disks. All these red points, they are centers of maximal disks. So at those points, for instance, at this one, I cannot find a disk that is bigger than this one, that is 3 times 3, and that is fully contained in the image and fully contains the one here in red. Okay, so all those red points are the locations of the maximal disk, and that is called the raw skeleton. So this is more. Okay. How do I get to those points? So that should be an easy way. So you take the original image, you don't do anything, okay, so you keep it as it is. Then you roll with size 1, so it is the set times set, so the set 8, this is set 8, so it is 1 on each side, so you have the center, 1 to the left, 1 to the right, so you're eroding with that. Now you erode with a disk of size 2, so 2 in radius. Now with a disk of size 3, 3 in radius, so the kernel is 7 times 7. So this is what is shown here. So this is the square of side 3, side 5, side 7. So you have the different erosions. Okay, so now you do an opening with that disk. Okay, so first you erode, and you do so you erode with 0, but you don't do anything, and you do an opening with 1. So you have an erosion, and you do an opening with 1. Erosion, opening with 1. Erosion, opening with 1. Okay, now you compute the difference. So what is the difference between this one and this one? So these 3 points are the difference. They were in the original, but they were not in the opening. So these points are maximal disks of size 0. These ones are this one minus this one. All these green points, they were in the original, they were not in the opening. So they are centers of this one, of radius 1. All these points, they were in the original, they are not in the opening, so they are centers of size 2. and this is the only point of size 3. And now you take all these points, and this is the raw skeleton. So the raw skeleton computed in this way, it is disconnected. Now we have to connect it. But we already know the tools. So what you can do, what would you do? You could get rid of isolated points. So probably these points you don't want. And then you can dilate the rest and make them connected. So now you can post-process this raw skeleton. So isolated pixels you remove, and you know how to compute connected components. So you compute all the connected components of this, and all of those that are smaller than 3 pixels, that are these ones, you remove. So you remove these few points because they are very small. So now, and for these connected components, we have used this labeling that we did before. And now you dilate. So you dilate, and you compute the intersection with the other one, and you keep dilating and intersecting, and at the end, you will have this reconnected skeleton. So, any question about this? Let me see if in Nightfall we have some nice thresholding. So Nightfall, so that you get an idea of how we this. For instance, this is option. So in option, we can have, for instance, let's say this image here. I don't know if we can add noise or not. No. Yeah, we can put the threshold to whatever value we want. So let's say this one, we do it very high. The result is here. So for instance, here I was too strict, so let's move them. So now you have how you get from a gray image, how you get a binary image, and thresholding is the most difficult way. But in this thresholding, for instance, you have all these holes. So how can I construct a mask that contains fully this moon? I can use these operations we have seen today. More questions? Also, this application here, I like it a lot. This one. Very, very interesting. So, just with the raw operations, you lose information, but if you combine them in a clever way, then you can recover most of the interesting part of the image without losing, and you remove the noise around. Very good. Okay, so